Hello, welcome to the next section, chapter 1311. Today we're going to discuss Fourier series. This is the last video of the Calculus 2 sequence. Um, so congrats for making it this far. Fourier series is typically, honestly, in my memory, not typically taught for Calculus 2, um, but we're going to discuss this anyways. Um, Fourier series are really, really important series. They're found all over the place in higher level mathematics. We use these a lot in linear algebra and differential equations. Um, Fourier series are, well, we'll get into what they are exactly. Um, this was developed by a famous mathematician, Joseph Fourier. Fourier was a mathematician who was studying heat flow through solids. If my memory serves correctly, he was working on trying to build better cannons for Napoleon, the Napoleonic army. And so this led to his discovery of the uh, heat equation, right? The Fourier series is an infinite series that's comprised of sines and cosines. So we saw before that our Taylor and Maclaurin series and our power series, these were a bunch of power functions added together, creating a polynomial, right? For Fourier series, we're adding together a bunch of sines and cosines together, okay? Um, Sine and cosine are periodic functions. So Fourier series are work really, really well for periodic functions, okay? So they work well when I need to model something that happens continuously, right? Periodically. Um, it works well for things that may be discontinuous as well. And so it allows me to take a discontinuous function and model it with a continuous function, which is nice because continuous functions let us do things like differentiate, integrate, things like that. When we have discontinuities, we can run into some problems. So it's nice to be able to model something that is discontinuous with something that is continuous, right? So things like this might be heartbeats, right? Breathing. We see this a lot in signal processing, okay? In music, right? You'll have notes that'll it's on or off, right? It plays or it doesn't play. And so recall from our previous section, chapter 1310, when we were talking about Taylor and Maclaurin series, that a Taylor polynomial approximation to a function is a very good local approximation, meaning that I'm not within an interval, right, a radius of convergence, I know that my Taylor approximation, that my Taylor polynomial is an exact fit to the function that I want. Outside of that radius, right, outside of that interval of convergence, that's when I can start to have errors. That's when my polynomial no longer models my function exactly, right? Um, and so that's a good local approximation. And we saw that this is true, it's a good global approximation, meaning everywhere, if my radius of convergence is infinity. If my radius of convergence is not infinity, if it's, an actual interval, um, it's a good approximation for my function locally, right? So if you kind of think of that linearization that we have for a function, it's a linear, it's a first degree Taylor polynomial, and it only really is good at estimating our function near our point of interest, right? So we have an interval of um, of convergence on that interval. It's great. Outside that interval, that's where I'm getting issues, right? Fourier series, again, are made out of sine and cosine. These are periodic functions, okay? So they're not necessarily good local approximations. The Fourier series is not a good local approximation. It is, however, a good global approximation. Um, Now, does that mean it's going to fit everywhere exactly? Not necessarily. So typically a Fourier will have error that's visible, like you can actually see it on a graph. Um, but it gives a good approximation over the entirety of whatever it is I'm studying. Okay. So again, there may be noticeable errors in value in the majority of the graph, but over the life of the function, it gives us a good approximation. It lets me know what my function does pretty much over its entirety. Okay. So let's go ahead and look at some of what I'm talking about, right? There's just a lot of text on the screen right now. So let's compare Taylor polynomials and their Fourier partial sum approximations as well. Okay. So we saw this previously. I actually went to Desmos and I had, you know, graphed this out. So this is just our Taylor polynomial expansion or approximation from the previous chapter, right? 1310. So for linearization, it's not a good approximation. It is when I'm close, but not when I'm far away, right? So it's a good local approximation. And then as the degree of my Taylor polynomial got larger and larger, I'm getting a better and better approximation to my function, right? So the 11th degree approximation has a really good approximation, and then it gives me errors. Okay. The Fourier partial sums for e to the x on this interval will be shown. Now, I want to preface this real fast by saying again, sine and cosine functions are periodic. So for Fourier series are good for approximating periodic functions. Okay. Um, they're good global approximations. So we went here through the Taylor. So on a chosen interval, okay, symmetric interval here, we're going to look at e to the x, right? And how our Fourier approximation, our Fourier partial sums will approximate our functions. So a first degree Fourier is made up of sines and cosines. So I'm going to just have a wave function, right? Obviously not a very good approximation. For S2, okay, this is the second partial sum. I have slightly better, right? So if we look at S1, it doesn't hug my curve at all, but it's, it kind of follows it in general what it's doing. A second approximation stays a little bit tighter, right? And then so forth and so forth and so forth. And so for S5, again, we're really looking at negative one half to one half and how closely it's approximating my function. Sine and cosine, again, are periodic. So we see that periodicity happening over and over and over again. Okay. A Fourier series has the general form of f of x equals a naught plus a1 times cosine x plus a2 cosine 2x plus a3 cosine 3x, etc., etc., plus b1 sine of x plus b2 sine of 2x plus b3 sine of 3x, etc., etc. So we're adding cosines and sines together. There's a lot of symmetry in what's happening here, right? I have coefficients for my cosines that are go by a, and then whatever index. And then for sines, my coefficients are b's, right? So when I sum these together, I get a naught plus the sum from 1 to infinity of an cosine n x plus bn sine n times x. Okay. The coefficient here is an. So we're choosing to start from 1 because this a naught doesn't have a sine or cosine. It's our constant here, right? So we assume that the series converges and that f of x is piecewise continuous on negative pi to pi. So piecewise continuous means, I can have jumps, but I can't have an infinite number of discontinuities within this interval. Okay. Our Taylor series that we went over in chapter 1310, we found by looking at derivatives. Fourier series are found by using integrals. So we have the integral from negative pi to pi of my function is going to be equal to me integrating this entire series from negative pi to pi, right? So negative pi to pi for a naught and with respect to x, and then I can just integrate this entire sum instead of looking at it piece by piece, right? So I would be integrating the series. Now, the nice thing with integrals and summation formulas is that they are interchangeable, okay? So the integral of the sum is the same as me taking the sum of integrals of cosine and sine, right? I'm summing the constant terms and I'm integrating the function, okay? Here, a naught from negative pi to pi is just 2 pi, right? So 2 pi times a naught, that constant, and then I have the sum of my an terms, right? My coefficients, because I'm it's like factoring out coefficients, although that's not factoring. I'm integrating, however, my function, right? And then same thing for here. I'm summing up all the coefficients of Bn um, times the integral of each of these sine to the n x's. So let u be nx, okay? Then du is n dx. And to solve for dx, I have 1 over n du, right? So we'll do a quick substitution here. So this is 2 pi a naught plus the sum of these an terms. And this cosine here is equal to 1 over n, okay, from this 1n. And cosine turns into sine, right? So when I integrate this, I get the sine of u, which when I replace the u, I would just replace it back with nx. So we've seen this a million times, so kind of skipping some steps here, but you should be able to keep up with that. We evaluate that from negative pi to pi, right, on their bounds. And we do the same thing for the next piece, right? However, sine, when we integrate it, gives us negative cosine. So we have this 1 over n from the substitution, and then cosine from the integration, and this negative pi over pi, right, for the bounds. So we'll go ahead and evaluate those. Okay, so we have 2 pi a naught. Sine on pi has values of, let me just think real fast, right? I always think of the sine function. So it starts at 0, and at pi is 0, and every multiple of pi is 0. Okay. Cosine starts at 1, and every multiple it's either positive 1 or negative 1. Okay. Or it's always positive actually. So we have 2 pi a naught. So here I have an times 0. Again, the 0 is because sine is 0 at pi and negative pi. So this whole thing will end up going away. And here at cosine, I'll have, remember it's negative 1 over n. So at pi and negative pi, I'm going to have values of negative 1. Okay. So when I plug these in, what happens here is a negative and a negative. So this is positive, negative and a negative. So this is positive. And then I have this negative here, right? So I have a positive minus positive. So that also goes to 0. And all I'm left with is 2 pi a naught, which is really nice. Okay, so everything falls out. Therefore, if I solve for a naught, okay, remember what we're equal to here. We're equal to the integral of negative pi to pi of f of x. And that is equal to 2 pi a naught. So solving for a naught, a 0, I divide both sides by 2 pi, and so a naught is 1 over 2 pi, and the integral from negative pi to pi f of x dx. So the first constant in my series can be found by forming this integral, right? 1 over 2 pi, and then from negative pi to pi of my function with respect to x. To find the rest of the stuff, right, when n is 1 or larger, we're going to first start off by multiplying both sides by cosine. We're going to use m of x, not n of x, right? So a different constant multiple of x, where n is 1, 2, 3, etc., etc. Okay. And also sine m of x separately. So when I say separately, I mean first we'll do it by cosine. We're going to do some stuff, come to an answer. And then secondly, we would do everything we just did with the cosine, but with sine. Okay. So we're going to multiply both sides by cosine m of x everywhere, integrate both sides, solve, and then we'll do the same thing again, but with sine of mx. Okay. So here, first and foremost, multiply both sides by cosine mx. So this function gets multiplied by cosine, and then we take the integral. A naught and the sum is going to get multiplied by cosine m of x, and we're going to take the integral. Okay. So obviously we're interested in the right-hand side more so than the left-hand side. So when I distribute this cosine in, okay, a naught is a constant, so I can pull it outside of the integration. I have cosine m of x. Here I will have, we already saw what we are allowed to do with this integral. So I have the sum, I'll have the integral of the sum of an cosine n of x, cosine m of x. And the same thing with the sine part. So here we'll go ahead and just swap the order right away because the integral is what I'll be calculating. So I have the sum of the constants times cosine n of x times cosine m of x, because I had to multiply this into the sum. Okay. And so I will add to that the sum of b to the n times the integral of sine of x, uh, n of x, and cosine m of x. Okay. So what we've done is we've taken cosine m of x, we've multiplied it times everything that we have, and then we're going to integrate both sides from negative pi to pi. All right, so we're going to actually find these integrals, okay? Whittle our stuff down as much as we can, simplify everything, and then we're going to do this exact same thing. I say we, but really you guys are. This exact same thing, but instead of multiplying cosine of x everywhere, it's going to be sine m of x everywhere. Okay, so I'm really only doing half of this for you guys, and I'm leaving the other half for you guys to do as an exercise in your classwork for those of us who are in my class. For those of us who are watching just because they like my stuff, thanks. Um, but also try that yourself. Okay, and you'll see. I put the answers here already, so you'll be fine. You'll be able to check your work. Here we're going to use the trig product to sum formulas in order to calculate these integrals, right? I have cosine of n of x times cosine m of x. These n and m's are not necessarily the same, and they're not necessarily different values, okay? As I go through the sum, they'll change, right? So here we're going to use trig product to sum formulas. These are those formulas. Cosine A times cosine B, right? Where again, two different cosines on two different inputs inside of a cosine is 1/2 cosine A minus B plus cosine A plus B. For sine times cosine, which you see here we have on the second part, that formula is 1/2 sine A plus B plus sine A minus B, right? So these formulas will allow us to integrate much easier because I'm taking a product of cosines or sines and cosines and turning them into a sum of cosines or sines, which are much easier to integrate. So focusing on just these two integrals that we have, right? So again, um, on my right side, right, it's this integral, cosine n of x, cosine m of x, and sine n of x and cosine m of x. I'm just going to calculate these integrals. The first one, cosine n of x, cosine m of x, using the trig product to sum formulas, I can rewrite this as 1/2 times the integral from negative pi to pi, cosine, the difference between those inputs, okay, plus 1/2 times the integral of the cosine where I'm adding those inputs, right? Obviously, I have a common term here of x that I can pull out. So I'm just going to let u equal that constant term n plus or minus m. I'm saying plus or minus because I'm doing these both at the same time, okay? And then my x is here as well, right? So I just went ahead and factor this, but I'm doing this for both of them, and I'm just going to take both cases at once by using the plus minus sign. I'm going to differentiate both sides. So I have du is n plus or minus m dx. And then I can divide both sides by this n plus or minus m. So I have 1 over n plus or minus m du equals dx. I make that substitution. And I'm going to have 1/2 this n plus or minus m on the bottom. However, for this one, the first one, it's minus. So I'm not writing plus or minus. I'm writing the one I have. For this one, it's going to be minus. Okay. The integral here for cosine is going to give me sine n minus m, and I'm going to evaluate from pi and negative pi. For this next one, it'll be the same thing, be 1/2, but it'll be not plus or minus. This one is plus. So I have, okay. So we have 1 over 2 and plus m sine n plus m to the x evaluated at pi and negative pi. So this is going to give us 0 for both because sine at any constant multiple of pi is 0, right? So 0 minus 0, 0 minus 0, all of this just goes away. So that's our first one, right? So if we come back to what we had here, this we're not dealing with this a naught just yet, right? Although this will go to 0 as well, it's cosine. This first one goes to 0, right? We had the cosine times cosine. So when we did that first, we got 0, okay? Now notice that we can't even do this if n and m are the same value. If n and m are equal in value, I have a 0 in the denominator here, right? In this substitution that I would make, and I wouldn't even be able to do any of, well, not any of this. I couldn't do the negative side. Okay, so this only works if m and n are not equal. Remember, n and m are 1, 2, 3, 4, etc., etc., etc. So they take on integer values, so I don't have to worry about adding them together and getting a 0 for something like this, right? It's only if I'm subtracting them. So if m is not equal to n, this whole thing goes to 0. Okay. Now what happens if we are equal to n, right? If those two values are the same. Well, this integral that we have that we uh, separate into something easier using that product sum rule, this would just be 2n or 2m or whatever, right? It's the same value being added together. Here it would cancel out to be 0. Okay. Cosine of 0 is always 1. Okay, its cosine starts at 0 at 1. So this would then turn into just 1/2 times the integral of negative pi to pi. Okay. This one we know drops out to 0 because we already did all of the work here. So I'll keep it, but we don't have to actually do any of it because we know any multiple of pi for sine is 0. So it doesn't matter how this ends up changing, right? Because this is again 2n or 2m, so it's really 4n. Here this is n plus m, so if they're both n's, it would be 2n, so sine of 2nx. This goes to 0, we know this already. This is going to be 1/2 x evaluated from negative pi to pi. Okay, so this goes to 0. This is 1/2 x negative pi to pi. So if I plug in pi and then I subtract the negative pi, that's basically pi over 2 plus pi over 2, okay, which gives me pi. So this integral is 0 if n and m are not equal in value, and it's equal to pi every time they are equal in value. So that was our first integral, right? So remember, there's another integral for us to work with, the sine times cosine. We're going to go through the exact same process that we just did. We're just going to integrate it using that product rule, right? So sine of x, cosine of x, you come here. That rule was the first entry and the second entry. Instead of subtracting on the first and adding on the second, it's added on the first one and subtracted on the second. Okay, here we go. Really doesn't make any difference, to be honest. So I have 1/2 negative pi to pi, n plus m plus 1/2 negative pi to pi sine of n minus m. Right, and again, we want to consider the cases whenever possible for these general values of n. So let's go ahead and start to do this, right? So again, using the same u substitution as before, I'm going to have 1 over 2n plus m. Sine, when I integrate it, will give me a negative cosine, and I'll evaluate that from negative pi to pi. And then that second term will look very, very similar, right? I'm going to subtract from that um, this 1 over 2 n minus m cosine from n minus m. So note here that we're adding them, and so here we're subtracting them because I get a negative cosine when I integrate sine. Okay, so this is going to give me 0. We saw this already, kind of what happens. Um, n plus m, any constant multiple of pi is for cosine, and negative pi is going to give me that 1 minus 1 stuff that we had up here that we calculated earlier, right? For this first integral. Okay, so we have the same thing going on. We're looking at 1 over n cosine n of x, a constant multiple of x. So at pi and negative pi, we get these negative ones and -1 and -1. Let's see here. Okay, so this goes to 0 and this goes to 0 as well. So they both go to 0. Okay. Using the results that we just calculated, okay, my function times cosine m of x from negative pi to pi is going to be a naught times the integral from cosine m of x dx plus the sum of my a n's from negative pi to pi, cosine nx, cosine mx with respect to x, plus the sum of the bn terms from negative pi times the integral from negative pi to pi, sine n of x, cosine m of x dx. Okay. So this is our formula that we have, right? We multiplied everything by cosine n of x and we're taking the integrals. Now we've actually calculated these integrals. Um, so this a naught term, I know we didn't actually go through and do it, but we already know cosine, the integral of cosine from negative pi to pi. Uh, we know that that goes to zero, right? We saw that. We've calculated it about 3 times already. So right here, one more time, right? When um, we do this for sine, we got cosine from negative pi to pi. Sorry, this is what I wanted to reference, right? So a single cosine, constant multiple of cosine, we integrated from pi to pi. We saw that it goes to zero, right? Same thing here, it went to zero. Here we were assuming that n and m weren't equal to each other, right? So constant multiple of x inside of the sign, we get nothing. So we didn't really have to do the work for this first one, because I know this goes to zero. Okay, the middle part we saw goes to pi if these things are equal. This one, the second part goes to zero no matter what the case is, whether it's equal or not equal, it will always go to zero. I think in the classwork, I asked you to verify that as well. So here I just kind of wrote what it equals to. We didn't actually go through the cases. For those in my class, I ask you to go through the cases of n equals m, m and n not being equal, et cetera, and show me that this goes to zero, right? Here, all the terms go to zero except for when n is equal to m, and that's why we have a sub m. Okay, so for all of these sums, it all goes to zero except for the specific case when n and m are equal here. And so that's why we wrote a subscript m pi. So I have that this integral here is equal to a subscript m pi. Okay. And for this case, we know m and n are equal, so I can interchange m and n whenever I want to. Okay. So this f of x cosine m of x dx, I'm going to write as a n pi since n is equal to m. Okay, so I really should have made this substitution here instead of just the a n, and I don't like the way that that looks, so let's go ahead and fix that. All right, that's better. Okay. So my a sub n is equal to, just dividing both sides by pi, so 1 over pi times the integral from negative pi to pi of my function times cosine n of x. Again, since I swapped these because they are equal in value. N counts by ones, right? 1, 2, 3, et cetera, et cetera, et cetera. Okay. So now we have a formula for a naught. We found a formula for a n. Similarly, we can find, you try for those of us in our class, right? Or not. If you're in my class, however, this is part of your classwork. Try to find the same thing for b to n, right? So if I do the same thing I just did to a n, I can find the general coefficient term for bn to be 1 over pi times the integral from negative pi to pi of sine n of x dx, okay? Where n is 1, 2, 3, et cetera, et cetera, et cetera. So this brings us to our definition. So let f be a piecewise continuous function on the interval from negative pi to pi. Then the Fourier series of f is the series a naught plus the sum from n to infinity of a sub n times cosine n of x plus b sub n sine of n at x. So we saw this already, what it looked like written out. Where my coefficients, a sub n and b n in this series is defined by the integrals a naught being 1 over 2 pi of my function being integrated from negative pi to pi. A n is 1 over pi times the integral from negative pi to pi of my function times my cosine times n to the x. So whichever coefficient I'm on, right, is the value that goes in this cosine. And for the b's, it's 1 over pi times the integral of negative pi to pi of my function times sine whatever n value I'm on of x with respect to x. Okay. So a lot of work goes into these calculations because you got to do a bunch of integrations, right? Um, and these are called the Fourier coefficients of f, right? Putting it all together, we have the following. My function can be approximated with 1 over 2 pi. So this is a naught plus this first sum here. Okay, notice I have f of x cosine of x dx. That is the coefficients, a sub n, and I multiply that times cosine of x. The next one, this is my the sum of my coefficients. This is b's, the 1 over pi, integral of f of x sine of x here with respect to x. And then I multiply after I find these times sine of n to the x. So whichever interval I'm on, right, whichever number of n I'm on, don't forget to multiply that. Okay, here we go. Sorry about that. So notice we're not saying here that f of x is equal to its Fourier series. It's a global approximation, right? It's not necessarily the same. It can converge. It can. We're not saying it doesn't, but generally speaking, it just gives us a good approximation for the global behavior of what we have, right? So let's look at an example. The square wave function is often used whenever we need to model something that consistently alternates between two or more pulses with a regular period. So when I say two or more, so pulses or states, right? We see this a lot in electronics, okay? Things like flow, like current flow through a circuit that's being turned on and off at a regular interval, so like an Arduino or something like that, okay? Um, so before we get into the definition, so just think of anything that's like on, off, on, off, on, off, on, off. There's really no intermediary state between yes, no, right? And so that's what the square wave function is used to model, okay? When something's happening and when something's not happening. The square wave function is defined as the following. My function is 0 if x is from negative pi to 0, negative pi being an included endpoint, 0 is an open endpoint, right? If it's not 0, it's 1. So if you think about computers, right? On, off, right? 0, 1. So there's flow, there's no flow, right? I'm 0 when I'm off, right? And I'm saying that's from negative pi to 0. And then I'm on at some moment that I'll call 0 until pi when I would turn off again, okay? Here, this function is periodic, okay? It's periodic with a period of 2 pi. So this 0, 1, 0, 1, 0, 1, 0, 1, it alternates with a period of 2 pi, right? So this is what that looks like, okay? I'm off for a period of pi, and then I turn on for a period of pi. Off, on, off, on. And it's always the left endpoint that's included, right? So here I'm 0, and then I'm on, right? I'm on, and then I get turned off, okay? And then I'm off, and then I get turned on, right? So it's on, off, on, off, on, off. Here, a naught equals, again, 1 over 2 pi, the integral times our function. So since our function is periodic, okay, and split, right, it's a piecewise function, the first half is always 0 from negative pi to 0, and the other half is 1 from 0 to pi. So I need two integrals here in order to model one period of my function, okay? So again, we're really just calculating from negative pi to pi, so this interval right here. So when I'm 0, obviously that goes away. Here, this is going to give me 1 over 2 pi times x, and I'll evaluate from 0 to pi, okay? And that will just get me 1/2 because the pi's will cancel. So my a naught term here is 1/2. My a sub n term, my generalized term for the cosines, coefficient for the cosines, is given by 1 over pi, and then integrate from negative pi to pi, my function times cosine n to the x. So again, I need two different integrals. The first one goes to 0 because the function is 0, and the second function is 1, so I'm just finding the integral of cosine. We saw already from negative pi to pi, cosine goes away. But that's not necessarily true from 0 to pi, right? So here, I'll cosine, I take its integral, and I get 1 over n pi from a u substitution, sine n of x from pi to 0, which will give me 0. Okay. So if you're really, really familiar with your sines and cosines, you can use symmetry too, right? We know cosine starts at 1, and then when I get to pi, I'm at -1. So I have just as much area above as below, and it's very easy to tell that that's 0 at that point. Okay. For b sub n, I have 1 over pi, the integral from negative pi to pi, f of x times sine of x. So again, I need two functions. The first one just goes to 0. The other one is just the integral from 0 to pi of sine of x. I know the integral is negative cosine. Okay. I have to make some sort of a u substitution, so I end up with this n in the denominator in front, and I evaluate this from pi to 0. 0 I know is 1. Pi I know is -1. Okay. And so we get the following, right? So when I plug in cosine, I get 1 here. When I plug in pi, however, it's n pi. Okay, so this um, alternates in value for 0 to 4. Cosine n pi. This term that I'm trying to evaluate, right, will look like this because n to the pi for even multiples of pi is 1. Okay, I get an output of 1 for that. And so this will go to 0 because I have a negative and a positive of the same thing. And so that's 0. When n equals 1, 3, 5, when it's odds, for cosine, we will have -1 as our value. Okay, so for 1, 3, 5, this -1 over n pi, cosine n pi plus 1 over n pi, this thing that I got from evaluating from pi to 0. Okay, I get one case where n is even, right? It goes to 0. When it's odd, okay, it's a little bit different because this -1 will make this positive. So I get 2 over n pi, right? So bn's are 0 if n is even, and 2 over n pi if n is odd. Therefore, the Fourier series for the square function is 1/2 plus 2 pi sine of x plus 2 over 3 pi sine of 3x plus 2 over 5 pi sine of 5x, etc., until I get this generalized term of 2 over 2k minus 1 times pi, counting by odds, right? Sine, and then this is odds of x, right? My odd powers. So once I got a few terms in, you can see what the general form is. Remember, this 1/2 is separate because it's a naught, and so it's not generally included in the series. Okay. So if I wrote this um, as a Riemann sum, it'll be 1/2 plus, and then the sum of my generalized term. Okay. So the question now is the series equal to its function as k goes to infinity? So before we even do that, let's take a break. Not a break, but let's look at a small animation of the square function for sine and cosine so we kind of see what's happening. Right? As I add more and more and more terms, I get closer and closer to the true value. So the real question is, um, as I add an infinite number of terms, does my series converge onto my function, right? Or is it just always some sort of an approximation? So let's look. We'll answer this, but let's look in the animation first. Okay, so here we have the square wave, um, and what you're seeing in the red is the Fourier approximation as we get more and more terms added on. Okay, so obviously when we just have one term, we don't have a very good approximation, but as we continue to add more and more and more terms, you see that you start to get more, uh, you start to converge onto the function more and more. And again, it doesn't always converge, right? We do have some conditions that will let us know when this is true and when it's not. And that's actually the next thing that we're going to go over. So that brings us to the Fourier convergence theorem. So if f is a periodic function with period of 2 pi, and f prime are piecewise continuous on negative pi to pi, then the Fourier series is convergent. So, um, so the convergence is really based on the function that we have. Okay. The sum of the Fourier series is equal to f of x at all numbers x, where f is continuous. At the numbers x where f is discontinuous, the sum of the Fourier series is the average of the right and left limits. Okay, so basically what it's saying is that for the convergence theorem, the sum of our series is equal to our function everywhere that our function is continuous, right? When our function is not continuous, it's the average value between those discontinuous values. Okay, so in math form, it's 1/2 times f of x plus f of x minus. What are these plus and minus? This is just shorthand form for the left hand limit at x and the right hand limit at x. Okay, so whatever xi is for our discontinuity, right? As x approaches from the left, plus as x approaches from, I'm sorry, approaches from the right and approaches from the left, it's the halfway mark of both of those. So for our function, um, that we found that we didn't graph, which you saw me do, here I'm 0 and I'm 1. So at this continuous point, I take on the halfway point of 1/2. Okay. So applying the convergence theorem to our previous example, we have f0 plus, so approaching 0 from the right. The limit as x approaches 0 from the right, f of x is 1. And as we approach 0 from the left, from the negative side, that limit is 0, and the average between that is 1/2, right? So at x equals 0, the point of discontinuity within my interval, the Fourier series has a sum of 1/2. Okay? So um, we have 1/2, this should be a plus. Okay, that's better. So we have 1/2 plus the sum from k to infinity of 2 over odd numbers times pi times sine of the same odd number times x is going to be equal to f of x if x is not a constant multiple of pi, and it will be 1/2 if x is equal to a constant multiple of pi. And so our constant multiple of pi's are where those discontinuities are, right? Constant multiple of pi, constant multiple of pi, constant multiple of pi, etc. Okay. So that is our formula for the square wave function, okay, right here. So not just the sum, but it's conditional because of the convergence theorem. So we take on intermediary values at the point of discontinuity. What if the period is not from negative pi to pi, right? What if it's not a length of 2 pi? What if it's a different period? What if it repeats every 10, right? Every 10 units instead of every 10 pi, right? Um, so what if it's not even a measure of pi, right? So what happens if I have functions with period of length 2L, right? So no matter what my period length is, I can always think of it as being 2 of something, right? So if f is a piecewise continuous function on the interval from negative L to L, right? So we got two L's there. Its Fourier series is a naught plus the sum from 1 to infinity, an cosine n pi x divided by L. So it's changing the period so that it's a period of L. And bn sine n pi x over L. Okay. A naught, instead of 1 over 2 uh, pi, it's 1 over 2L from negative L to L. F of x. For n 1 or larger, a sub n is 1 over L instead of 1 over pi, right? It's 1 over L from negative L to L. And here it'll be n pi x over L. So when L is, when this is from negative pi to pi, this turns into nx, right? This turns into pi. This turns into just nx. So this is the generalized form. This is really what you normally will see and use in practice, because it's not always going to be from negative pi to pi. So everything is the same, but if we're to choose an interval of negative pi to pi, it would default back to the formula that we derived at the beginning. Okay. And so this is really what you will be using for Fourier, right? And that's a series. So these are my A sub n are given by this formula. My B sub n coefficients are given by this. Don't forget that once I find a B, I have to multiply it times that appropriate sine function, right? And once I find an A, I have to multiply it times its appropriate cosine function and add them together, right? So it's a long string of cosines and sines. All right, that's it. Hope you guys enjoyed these videos. Hope I didn't bore you. I will make a Calculus 3 at some point. I actually have all the lectures already written for Calc 3. I just have to actually uh, film them, but I never teach Calc 3, so it's not a high priority for me. However, I do teach statistics all the time, so my next project is a stats course, and I do want to go back and add more examples and all these kinds of stuff to these course readers. Okay. Thanks for watching, and I will see you on the next video.